outreach talk. So I shall try and explain it with as little mathematics as I possibly can. And please stop me if I'm going too fast or if there's something you want to know. So yes, I'm Mike McCulloch from Plymouth, and I'm going to be, let me just, talking about what inertia might be, what I think it is. I'm going to introduce quantized inertia, the theory of it, show the astronomical evidence for it, talk a little bit about the controversy and the debates I've had, and the DARPA funding that I've had as well, the lab tests, and then talk about the possibility of having electric rockets and things like interstellar travel enabled by this technology. Okay, so a bit about my background. So I had a BSc in physics at the University of York, PhD in ocean physics at Liverpool. I was a scientist at the Met Office for about 10 years, ocean modeling. And then I became a lecturer in geomatics, which is the maths of positioning in space at Plymouth University. And now, well, in 2018, I got some funding from DARPA, so I bought myself out of teaching. So I'm now a research-only lecturer at the University of Plymouth. And I've published about 25 papers proposing a new theory called quantized inertia. And I published a book as well called Physics from the Edge. Okay, so the basic problem that I was trying to solve in the beginning was that galaxies seem to spin too fast. So here's a galaxy. This is the Andromeda galaxy, and the stars are all spinning around. And if you point at one of them, so this yellow star here, then it's attracted toward the center with the by gravity, of course. This is illustrated by the black arrow. And also as stars spin around, they feel a centrifugal inertial force pushing them out. So that's indicated by the white line pushing out there. Now, given the amount of matter we can see in the galaxy, there's only a relatively small gravitational force pulling this star in, much smaller than the centrifugal force pushing it out, apparently. So what astronomers have done, or I should say this anomaly was discovered first by Fritz Zwicky, who's shown on the bottom left, in 1933 for galaxy clusters, and later by Vera Rubin in about 1980 for galaxies themselves. So the response of the astronomical community has been to add what they call dark matter to the galaxies. So they just add it to boost the gravitational force. So you can see that I've lengthened this black arrow here to show that it's now balanced with the centrifugal force, and everybody's happy about that. But I don't like dark matter at all, because I regard it as not scientific, because it's arbitrary and it's unfalsifiable, because you can look for more and more extreme versions of dark matter for your entire lifetime. So you can get a lot of funding, but you can go on forever. So other reasons to dislike dark matter are as follows. So there are several of them. There's something called Renzo's rule. And this, I think next month you have somebody, Stacy Mogoff, coming to talk to you, who'll be probably be mentioning this as well. Renzo's rule is that speed follows the light. And that means that when people look at galaxies and they see a variation in the rotational speed, that variation is always associated with variations in the light curve, the amount of light, stellar density we see. There's never any variation of the speed due to apparently something else. So that implies that dark matter does not exist, and that the dynamics is controlled entirely by the stellar matter, the lit matter, if you like. There's also something I call Milgrom's break, which I'll describe a bit later, but it's an abrupt change in the behavior of galaxies at a particular radius that's very interesting. Also, globular clusters can't contain dark matter because they're too small. Dark matter has to stay smooth on galactic scales, because otherwise it would just fall into the center of the galaxy. So they have to say it likes to be smoothed out. So they can't then say that it concentrates into globular clusters. But the interesting thing is that globular clusters show anomalies too. They also spin too fast. Also, wide binaries spin too fast. Twin stars orbiting around each other, and they certainly can't contain dark matter. There's a core crust problem. The standard model predicts galactic centers wrongly. There's no direct evidence for dark matter after 40 years of searching and billions of dollars spent on detectors. And also, and more philosophically, dark matter is not falsifiable, as I said before. You can look forever. You can invent different versions of it to look for forever, and it's a bit of a sinecure. And also, as I would say, quantized inertia predicts galactic behavior without it, as I'll try and show you. Okay, so inertia. So having rejected dark matter, I started to look at inertia, and the reason I looked at it was this was that Richard Feynman was very keen on it and pointed out that it's a mystery. So I'm just going to
taught me to notice things. And one day when I was playing with what we call an express wagon, which is a little wagon which has a railing around it for children to play with that they can pull around.
Okay, so as Feynman said, inertia has always been a bit of a mystery. And it's not due to the Higgs field, which is a relatively new idea, which only explains the mass of the quarks, which is about 0.1% of the total inertial mass. So what I'm going to propose to you now is that inertia arises from a kind of mix of relativity and quantum mechanics. So the first part of the mix is the Heisenberg uncertainty. So I've been told I shouldn't show any mathematical equations, but I had to show this one. So it's quite simple. It just states that the uncertainty in momentum, so this delta P here, times the uncertainty in position has got to be greater than some very small number. So this means practically that if you look at smaller and smaller regions of space, so delta X reduces, then the uncertainty momentum has to increase. So that implies that on the smallest scale, space is teeming with very energetic particles, what are called virtual particles. So I've tried to show that here. So they form in pairs to conserve momentum. So one comes up, one goes down, and they recombine a short time later and then reform. And in quantum mechanics, each particle has a wave as well. So I've shown that with the red sine wave here. So what we think of as a vacuum is not really a vacuum at all. It's full of these virtual particles. So a bit later, Hendrik Casimir, who's shown top right, he said, okay, if this is true, then we can test it. All we have to do is put two conducting plates very close together. So I've shown that with the two white vertical lines. And then some of these quantum waves, these red curves here, will fit between the plates. So you see this one has what's called a node on the plate. This means the field isn't moving at all. So the electrons in the conductor will not move to cancel the field. But with this one, the second one down, here we have an antinode. So the field is changing up and down. The wave is going up and down. So the electrons will cancel the wave. So this means that these waves will disappear. And that means now you have more waves hitting the plates from outside than are pushing out from inside. So there'll be a force inwards and the plates will move together. And this has now been seen. So these virtual particles really are there in the vacuum. So just to move on to an oceanographic analogy, imagine you have a ship next to a dock. There'll be a lot of waves out to sea on the right of the ship, but there'll be fewer waves for a similar reason between the ship and the dock, because a lot of them will be cancelled, in this case by friction between the water and the dock and the ship. So this means that more waves will be hitting the ship from this direction than from the other direction. So the ship will move towards the dock. So people on the ship might say, why is this happening? If they can't see the waves, they would not understand why the ship is moving. And I think this is what's happening with inertia. We don't see the quantum waves, so we don't understand why it's happening. But I'll try and show you that that is in fact what is happening. But first of all, I just have to introduce the concept of a horizon. So imagine that you're on a rocket accelerating to the right, and there's an explosion to your left. So boom, and you accelerate to the right. Now, if you accelerate fast enough, the sound from the explosion will never catch up with you. So then you could say that from your point of view, this explosion is behind an acoustic horizon for you. So that is the meaning of a horizon. It's a sort of limit to the space that you can know about. In this case, acoustically, but you can apply it to light as well. And Stephen Hawking thought a lot about this. So of course, if you have a very dense clump of matter, it will stop light escaping from a particular region of the cosmos. And the boundary of that region will be a horizon, because you don't know what's inside there. So this is, of course, a black hole event horizon. And Hawking wondered what would happen if you had one of these virtual particle pairs emitted right on the horizon. So one comes up and one goes down into the black hole. And we know that once it's in the black hole, it can't get out again. So that one disappears from the point of view of somebody outside. And this particle now has lost its twin. It can't recombine and cancel. So it gets emitted as Hawking radiation. About the same time that Stephen Hawking was doing this, Bill Unruh, who's shown on the top right in Canada, was thinking about accelerating spaceships. And he said that if you have a spaceship accelerating to the right, shown by this white arrow, then there's a horizon to its left, because light, limited to the speed of light, according to relativity, can never catch up with it if it's accelerating away. So there'll be what's called a Rindler horizon to the left of this accelerating spaceship. And in the same way, if you get a virtual particle formed on the Rindler horizon, the one that goes behind the horizon disappears, and this one comes off and becomes what's now called Unruh radiation. So this is a very strange kind of radiation, because you can be standing there in one particular region of space and somebody's accelerating past you and they can see a hot radiation surrounding them, but you won't see it. So this sounds very esoteric, but it may already have been seen. The problem with Unruh radiation is that its wavelength is so massive. So I've shown an equation here for the wavelength. This is the wavelength, this lambda symbol here on the left. And you can see it depends on the speed of light squared, which is about 10 to the power 17. So for a normal acceleration, this A on the bottom is the acceleration, the Unruh waves are about 7 light years long, and we can't see radiation like that. But for very high accelerations, they might be short enough to be seen, and that would be a good test. And the highest one of the highest accelerations ever produced was using a gold nanotip. So I've shown it on the top right here. They shone a laser on it, watched the energy propagate around the very sharp tip of the nanotip, and the acceleration was very high. It was about 10 to the 20. And they saw radiation coming off, which looked like Unruh radiation, and this was pointed out by Smolyaninoff in 2005.
Is that a photograph of it? Is that little gold photograph? Is that a real photograph?
The top picture is a photograph, and the second one is also a photograph. The bottom one is a schematic, of course.
Nice.
Okay. So this Unruh radiation could well exist. It may have been observed, and so I'm going to use it to try to produce a model for inertial mass. So imagine you have an object accelerating to the right, this black circle. So because it's accelerating, it sees both the horizon to its left. So this black area on the left is the region it can't see. And it also sees these Unruh waves all around it. So it sees Unruh waves in front, and I've shown that with the red sine waves in front of it. But it sees fewer of them. It'll see fewer of them behind it, because rather like the ship and the dock, they'll be damped by the horizon. So this is the big innovation, I suppose, that I'm trying to do. I'm saying that relativity, in other words, horizons, can interact with quantum waves, which is very new and radical, but as I'll show you, it seems to work. So this object sees more Unruh waves in front of it than behind, so they tend to push it back against whatever acceleration it has. And I showed in a paper in 2013 that this predicts inertial mass, the pushback against acceleration. I must admit I made a factor of 2 error in this paper, which was corrected by a colleague of mine called Xiaomei Jinnei later on. Okay, so this predicts the inertia we know and love, but there are some differences to this model that make it testable. It also says that when the acceleration is very low, incredibly low, about 10 to the minus 10 meters per second, then the horizon retreats backwards almost as far as the cosmic horizon. So the cosmic horizon is the part of the universe that's moving away from us so fast that we can't see it anymore. So it's very far away. It's about 10 to the 26 meters away. But because the horizon and the cosmic horizon on both sides are now about the same, there is no asymmetry in the radiation on both sides of the object. So the mechanism for inertia that I've just outlined collapses. So this means that for very low accelerations, there is no inertial mass. And I proposed this in 2007 in a paper back then. But this is exactly what we need to explain galaxy rotation, because in the center the stars are accelerating quite rapidly around. Towards the edge they're moving more sedately, and the acceleration is much lower. So what this model does is, for these stars at the edge, it reduces the inertial mass, reduces the centrifugal force, and it does it by exactly the amount needed to balance the gravitational force. It's exact straight away, and there is no adjustability in the theory, so that's a very good indication that it's correct. So I showed that in a paper here in 2012, and also a paper here in 2017. And the data is shown in this graph. So on the x-axis we have the expected acceleration of a galaxy, and I've taken data actually from Stacy McGough. I took some of his data that the guy is going to be talking to you next month, and the observed acceleration of the galaxy is shown up here, and Stacy McGough's data is the grey squares, and what I'm proposing is the dotted, the dashed line here, which goes through the squares, so it agrees with the data. There is another theory called MOND, which is shown by the solid line, but the disadvantage of MOND is that it requires a number to be put in. You have to put in a number to make it work, whereas what I'm suggesting doesn't require any arbitrary numbers to be put in. It works all by itself. Okay. But there's an even greater proof that it has to be what I'm saying, and that there really can be no doubt, and that's shown here. So this is a galaxy. This orange blob is supposed to represent a galaxy. In the center, the accelerations of the stars are high. So if you follow the white dotted line down, you see the short Unruh waves that are seen by the stars in the center. As you move out to wider radii, the acceleration is lower, so you see longer Unruh waves. But at exactly the radius of the galaxy that the Unruh waves reach the Hubble horizon, that they become the same size as the Hubble scale, that is exactly the radius at which the galaxies start to misbehave. So this is a very clear indication that it has to be Unruh radiation doing it, and it has to be quantized inertia, because no other theory has that characteristic.
Sorry, Mike, I didn't understand that. Would you mind just repeating what you said, please?
Yeah, so so in the center of the galaxy, the stars are milling around with high acceleration, so they see short Unruh waves, and I've shown those at the bottom here with the tight sine wave. As you move out to the edge of the galaxy, the acceleration reduces because the acceleration is v squared over r. So you see the stars see longer Unruh waves, and at exactly the radius at which these Unruh waves become long enough, they're at the Hubble scale and are being damped by this Hubble horizon. That's the radius at which the galaxies start to misbehave, and the dynamics changes abruptly into the anomalous one.
So you're saying that the radius that your theory predicts is indeed the actual radius that the effect starts to appear at?
Yes, that's right. And that's a very clear indication, because there's no adjustability in the theory, so it can only predict one thing, one radius, and it happens to be the correct one.
Would that be the Hubble horizon? So the Hubble horizon, that's the horizon that we can see, so the kind of observable universe, is it?
Yes, that's right.
And so would the Hubble horizon be the horizon that the galaxy would see, or that we would see? I think, because obviously they'd have so the galaxy, if they're in different locations, they'd have a different kind of Hubble horizon than us.
This is a Hubble horizon that's predicted by looking at the acceleration of all the galaxies away from us.
Okay.
The cosmic expansion, and at some radius away from us, they're moving away from us at the speed of light. That is taken to be the Hubble horizon.
Yeah. Okay.
And it assumes that our Hubble horizon from us is the same as its Hubble horizon from it.
Yes, so everybody should, well, of course we don't know, but everybody should have the same Hubble horizon, because everything is accelerating away from everything else equally. Okay. Does that make sense?
Yes, it does. Thank you.
Yeah. Okay. Okay. So that's galaxies. I've also looked at wide binaries. So a wide binary is two stars that are very far apart. So 7,000 AU in this case, but they are still bound to each other. And the great thing about them is that dark matter cannot be added to correct them, because, as I said before, it has to stay smooth on large scales. So it's a perfect test. So I got my postdoc, Jesus Lucio, who's shown here, to produce a model of a typical wide binary. And he modeled it with three different versions of physics. First, in blue, Newton or general relativity, which are on this scale about the same. And then in green, Mond, and then in red, quantized inertia. So because we know wide binaries are stable and bound, which of these models will show that the wide binary is stable and bound? Well, I guess you can guess, because otherwise I wouldn't be showing you. But I'll play you you can see that quantized inertia predicts that they're bound, whereas Newton, general relativity, and Mond predict that they just move away from each other. So that's also a nice derivation, some nice evidence for it. Okay, so it's all right predicting things that have already been seen, but it's good for scientists to be a little bit bold and try to predict things that haven't yet been checked. So I've tried to do that in the next two slides. So these are a few predictions for what might be seen if the theory is correct. So for example, there should be a radial variation in dynamics. So at certain radii in the galaxy, as you go out, the Unruh waves do fit within the cosmic horizon, and at certain radii they just don't, because the waves don't fit. So there should be some kind of dynamical variation radially outwards through the galaxy. There should also be rings around astronomical systems when the acceleration gets down to this value, because, and this is something called Hoag's object, which I think is quite famous, and some of you may have seen in your telescopes. So it's obviously a ring around a star. So the idea is that as things move out from the star, their acceleration reduces and the inertial mass reduces as well, so much so that at some point their inertial mass is so low that they can be pulled back by the star. And so you tend to get this ring. Also, the theory predicts that early galaxies should spin faster for the same mass. This is an interesting prediction because the theory depends on the cosmic scale. So in the past, when the cosmic scale was smaller, the inertial mass was different in the theory, so you should see different physics. And when I made this prediction, they haven't actually looked, and now a few papers have been published to show that this is in fact true. Okay.
So what does that mean? Does that mean that the dark matter from early galaxies has evaporated or something?
Well, of course, it's not dark matter, if I'm right. It's a change to the dynamics, but...
No, I'm asking for the classical explanation.
Oh, I see. So I guess most astronomers would say that there must be more dark matter in the earlier galaxies. And yes, so it's evaporated later on. Okay, I'll just discuss a few of these. So number 6 is that inertial mass should reduce along spin axes. So this is a prediction I made, that if you're in the center of something spinning, if you're along the spin axis, the mutual acceleration between you and the object should be virtually 0. So you should get a phenomenon that looks very much like galactic jets. And I've shown a picture here of a jet. This isn't actually a galactic one, it's a stellar jet. But you should expect to see things like this along spin axes of astronomical objects.
A quick question: what's a spin axis? Like, what's a spin?
So if you have a ball that's spinning, it's the axis of symmetry of the ball.
Oh, okay.
So the Earth has one. It goes roughly through the poles.
Is that why quarks have spin? I'm just curious.
Well, that's rather different, because quarks are subatomic particles, and spin in physics very often doesn't necessarily mean physical spin.
But quarks also have an axis of spin, and so do electrons. Anything that spins has an axis that it spins around.
Yeah, that's right.
Okay, nice. Thanks.
Okay. And also GPS satellites should show a latitudinal anomaly in their dynamics. That's because when they're over the pole, or closer to the pole, their mutual acceleration with respect to the Earth should be different.
Sorry, did you miss 7?
Sorry?
Did you miss number 7?
Oh, yes. I'm just going through a few of them. Number 7 is that isolated objects should spin in the same sense. So it's a consequence of the theory that things in deep space, because their acceleration is so low, the Unruh waves should start to interact with other similar objects in deep space, and so they should all be spinning in the same direction.
And is that true?
Yes, it is for quasars. Recently, that has been noticed. The quasars are all spinning in the same direction.
Fantastic.
So that's nice. And then a few other ones. An interesting one that I published recently is rapidly spinning objects should not be able to perceive the sun. So the idea here is that if you accelerate something by spinning it very rapidly, then the Rindler horizon will come closer to it than the sun is. So they will then not know anything about the sun. And so presumably they would not be able to, they would not be under its gravity either. So I've made a few predictions for experiments that could be done there as well. And then number 11 is important because the theory says that two bodies dropped together should fall to the ground together, which satisfies the equivalence principle, but they will both move slightly more quickly. What else? Now I can look at the number 16. Unruh waves from highly accelerated bodies may be damped. So this is an interesting one because it means that if you highly accelerate an object, you might be able to use radio waves or some electromagnetic radiation to interfere with the Unruh waves it sees and change its inertial mass that way. So I suggested an experiment for the particle collider at CERN, that they could accelerate a particle around the loop and then try to interfere with its dynamics with radio waves. Okay, so just a few predictions to show that this theory is predictive, and that I'm trying to be bold and make predictions that way. Okay, so the big thing here is that if we understand inertia, we can control it for the first time. So for example, if you have a very highly accelerated object, a spinning disk or something, and you spin it fast enough, it'll see Unruh waves that might be short enough to be damped by a metal plate, which I've shown with the blue line here. And then this acceleration core will see waves coming from all different directions except from above, and so it should move up. So this is a kind of propulsion then that doesn't require fuel. Normally we need a rocket. We burn chemicals in here. We fire the hot exhaust downwards so that the conservation momentum takes us upwards. But with this, you don't need any fuel. You would just need a damper. What you're effectively doing is making a gradient in the 0-point field, the quantum field, and then this object is moving down the gradient, which happens to be up. So this is something I call a horizon drive, and it's a propellantless alternative to rockets. So how might you do this? Well, it's no good having a very slowly accelerating object, because the Unruh waves will be light years long, and they won't interact with a metal plate. They use very long radio wavelengths to communicate with submarines, because very long waves penetrate through most things, including metal. What you need to do is have a very highly accelerated object, and then it should be damped. Then the Unruh waves should be damped by a metal plate on one side, and then the waves from the other side will push it back, or push it in any direction you want. So I published a couple of papers on this sort of idea. So knowing this, a sort of pattern started to form as I looked at more practical experiments that had been done. So some of them are quite famous. You may have heard of an experiment done by Pokletnov in 1994, which is extremely controversial. He had an asymmetric disk, which had a very fine grain on top and a very coarse grain on the bottom, and he span it to give it a high acceleration. And he saw that things in its vicinity moved upwards. Well, this is quite interesting because a very fine grain on top would damp the Unruh waves more than a coarse grain would on the bottom, because the cavities there are larger on the bottom. So you would have a gradient in the Unruh field, the quantum field, which would be more intense below and less intense above. So it tended to push things up. Also, Roger Scheuer in 2001, this is also very controversial. He had a copper cone like that. He resonated microwaves within it, so the microwaves are accelerating very rapidly inside. And he noticed that it seemed to move slightly towards its narrow end, which is still not accepted by many people. It's extremely controversial. But this too fits this kind of model, because you would have this wide end of the cavity would allow more Unruh waves, and this narrow end would disallow more of them. So again, you have a gradient in the quantum vacuum, intense on this side, less intense here, so things would tend to move down it and go towards the narrow end, as observed. James Woodward in the 1990s, he used asymmetric capacitors and he vibrated them using piezoelectrics to give them a high acceleration, and he noticed that they moved towards the thick capacitor plate. So it's a capacitor with a thin plate and a thick plate. And again, you'd expect a thick plate to damp the Unruh waves more. So again, you've got a gradient in this direction, so that kind of fits. And then Thomas Townsend Brown in the 1950s, he also used capacitors and sparks in them and showed that they move towards their anodes. And I'll discuss this a bit later, but that also produces a gradient in this direction, which would fit. So it seems that all these phenomena, which are extremely controversial taken by themselves, seem to be showing the same thing, which seem to be consistent with quantized inertia. So I got interested in trying to model them. So looking at the Emdrive, for example, this shows the thrust that several people have got out of the Emdrive. So the x-axis, the y-axis is the observed thrust in newtons, and the thrust predicted by quantized inertia for the Emdrive is shown on the x-axis. And you can see that the values are fairly close to the line. This is in my paper from 2017. Although having said that, there are about 3 tests that have been done since then which haven't detected any thrust from the Emdrive. So this is still very controversial. Okay. So it was when I started getting
Sorry, Mike, these numbers here,
yes,
these numbers here from NASA, for instance, are these accepted?
They're published in a peer-reviewed journal by Howard White, who's a NASA employee. So they are accepted but hotly debated. They were published in a good peer-reviewed journal.
Have there been a rash of attempts to replicate them?
There have been, as I said, 3 attempts since then that attempted to replicate them and have failed. So one by McDonald at the Navy Research Lab, one by Martin Timar, and also one by Howard White himself.
And he failed the second time?
Yes, he failed the second time.
And what does he think now?
Well, I don't know. He's not trying again at the moment. He's run out of funding, and also he's left NASA to set up his own institute. So I think he's snowed under with admin at the moment. But yeah. So as I said, there've been 3 null results. One of them I'll mention in a little bit. Okay, so you can probably see the danger of working in this sort of field, that the data, I'm not talking about astrophysics because the theory works very well there, and I'm very confident in that field. But as soon as I started looking at this lab data, I began to get into trouble. For example, members of the public started writing to my university, criticizing me and saying that I was wasting my time. And after a few of these letters, my head of department wrote a brilliant letter back to one of these people, saying that they obviously disagree with the concept of academic freedom, and he was pointing out that I've won best of awards for 2 years running in a very good journal, and it's possible that they're better informed than their editorial board, but he had some doubts. So this is a fantastic letter to from my head of school. So I was very pleased about that. But then the preprint archive, I don't know if you know about that, but every physicist around the world, when they have a paper accepted by a journal, or even before, they put it in this preprint archive so everybody can see it for free, and so information can propagate through the community most rapidly. So about the same time as I started looking at these thrusters, I was censored by the archive. They started refusing to accept my papers, even ones that I'd published in peer-reviewed journals. So I had to move to ResearchGate, which doesn't have this kind of censorship. I also started getting very interesting lampoons online. So one website made me out to be Dr. Mickey Mouse, and there were lots of comments online saying that if I could get my papers into a proper peer-reviewed journal, they would cut it to ribbons because he's not preserving the Einstein equivalence principle. But the person writing it doesn't know that I've already published 25 papers in very good journals. So, and also I was accused of crackpottery and all sorts of things like that online on Twitter. And Forbes magazine wrote quite a severe criticism of the theory. Ryan Koberlein, that I disagreed with, but they wouldn't let me write a disagree with, is that he said to be a viable model, MISC, which is quantized inertia, will have to address its contradictions with established theories. But in my opinion, that's wrong, because the only valid criterion is tests against data. So I think this shows some problem with physics, and that theories are extremely important to people, and that they've forgotten that the ultimate test is against data. The point is that the standard theory has never predicted a galaxy rotation correctly without the addition of arbitrary dark matter, whereas quantized inertia predicts them all straight away and without any adjustment. So I disagree with this article anyway.
I feel like a lot of the time in, I think, scientific community in general, I do find if there's been a theory around for a long time, people do struggle to let go of it. And dark matter is something people have been looking into for so many years. I think, yeah, I think maybe part of it is just they don't want to let go of it.
Yes, I think that's right, and I don't blame them actually. I think skepticism is an important part of science, but I just like to point out to them that the only thing important is data, not beloved theories.
Mike, it's Nick. A sort of related question to Zach's, I think. If quantized inertia is another way of looking at the universe, and it therefore brings into doubt, the viability of dark matter, what role, or is there a role indeed in that model for dark energy? Because people always talk about dark matter and dark energy as a sort of a viable pair. Does that mean that dark energy is out the window, or what?
Yes, dark energy is also not required. So I didn't show you in the talk because it requires some maths, but you could show from quantized inertia in about 3 lines that a minimum acceleration drops out of the theory of 2c² over the Hubble scale. And that's the acceleration, the cosmic acceleration that they need dark energy to produce. So that drops out of the theory straight away.
So are you predicting the Hubble constant? Hubble parameter, I should.
I'm using the Hubble constant, which is an observed, well, I suppose it's semi-observed parameter.
No, what I'm saying is, if you plug in your values for the size of the universe and yada yada yada, and you come up with a minimum acceleration, is that minimum acceleration the same as h0?
Yes, it's linked to it, and I can predict an h0 from galaxy data. I could go the other way. So I could look at the way galaxies are spinning, and then I can predict my own version of h0 from that, which I haven't done, but I could do.
Well, there's an opening for you, because there's this argument about 68 versus 74.
Yes, that's true. Yes, I just haven't had time to get into it yet. At the moment, I'm just taking one of the values and I'm predicting galaxy rotation from it. But from the observation of galaxy rotation, I can predict a value and see which one is I agree with. So yes, you're right. I could do that.
Some of this argument kind of reminds me of Richard Feynman again and the Challenger 13 inquiry on the O-rings. And it was said that the O-rings were still flexible at these low temperatures. But Richard, he took a sample of the O-ring material and clamped it and froze it. And when he brought it out of the freezer, it did not regain its original state, which it did do at a higher temperature. And of course, Challenger was launched at a lower than normal temperature.
Yes, that was a brilliant demonstration, wasn't it?
Yes, it really was. It's typical of him, though, wasn't it?
Yes, he was. Yeah, he was also a showman, as well as being a brilliant scientist. He was a showman. Okay, so all these criticisms evaporated actually when I was contacted by DARPA in the USA. So in 2017, one of their line managers wrote to me saying he was interested in my work, and I applied for funding and was awarded $1.3 million to try and demonstrate that quantized inertia could produce thrust. So DARPA is the US Defense Advanced Research Projects Agency. So they're tasked with making sure that the USA is not militarily surprised by any developments that are going on in China or Russia or other places. And in the past, they've come up with some good stuff. They had a hand in GPS, developing GPS. They developed the first version of the internet, which was called ARPANET. ARPA was the original version of DARPA. And they had a hand in the stealth project as well. So in 2018, they started to fund me to do two things: to make quantized inertia more predictive. They wanted a computer model based on it, and also to show in the lab whether or not it can counter gravity, which means produce thrust or launch things. So also people started joining in about this time. So this is a timeline of the year here showing the number of papers published on quantized inertia. So initially it's just me until about 2015. Then in 2016 I was joined by Jaume Gine from Spain. Then a Spanish scientist actually came to Plymouth to stay near to me to learn about quantized inertia, Professor Perez-Diaz. And then there was a paper by Keith Pickering, Travis Taylor, and other people have joined in 2019. So it seems to be taking off at the moment. So the DARPA project so far, so there are three main experiments I want to talk about, but I can't really say much about two of them. I'll tell you as much as I can. I employed a lab in Dresden, Technical University of Dresden, to do an experiment involving a light Emdrive. So an Emdrive using a set of microwaves, light photons inside it. So what they did was they took an infrared laser, they fired it into a cavity, a copper or a silver cavity. They tried both, and they had it on a torsion pendulum. So there's an axle here and a counterbalance there. And so initially they were getting results that looked just like quantized inertia, but recently they're saying they're not getting any thrust at all. So there's plenty I'd like to say about this, but I can't because I'm sort of awash in controversy with this one. There's a certain legal disagreement because the German lawyers think that I can't say anything about this experiment at all, and the lawyers at the University of Plymouth say that I can say virtually everything about it. So I'm simply not sure what I can say and what I can't, so I'm not going to say much at all. Just to say that I've abandoned this experimental pathway.
Mike, is it that the Germans published some results and then withdrew them? Is that what they're saying?
They didn't publish the results. They sent me lots of results, and then they went back on them. But their latest result was negative, so so all the earlier results were then void. But the main issue is that they don't want me to show any details of their experiment, because they say that impacts their IP. But according to the University of Plymouth lawyers, we own the IP. So I really don't know who's correct, and the lawyers are trying to sort it out at the moment. So I'm trying not to say much about it at all.
So but the point here is you ping a laser at a copper can, a slanted copper can, and you would expect the copper can to move away from the laser, but in fact it moves towards the laser.
Yes, the prediction is that it should move towards its narrow end.
But my intuitive prediction would be that it should move away because of the like that little light bulb with a black windmill in it. I've forgotten what it's called.
Yes, I know what you mean, but that's a much smaller effect. So the thrust from a photon is P over C, where P is a power in watts and C is the speed of light. So P over C, very small. The thrust due to quantized inertia expected is PQ over C, where Q is the quality factor of the cavity, which for the ones in Germany initially was very disappointing at 8. You can see the laser bouncing around inside here. Well, in Germany, in the first tests, it was only bouncing 8 times, which is very poor. I was hoping to have it bounce something like 1 million times, a lot. They improved that to about 40 by the end of the project. Okay, so the second experiment was done in Spain. So what they did was they had a laser fired into a fiber optic loop. So the photons are accelerating around very fast, presumably seeing Unruh radiation from all directions, except the Spaniards put a metal plate underneath the fiber optic to damp the Unruh waves on that side. That was the idea. And in their tests, they seem to be getting a force which is downwards and consistent with predictions of quantized inertia. And they then put a metal plate symmetrically on top, which should damp the Unruh waves all around it, so there should be no thrust. And there was indeed no thrust. So the results were looking good, but now we're not sure about the scale. The balance they're using seems very suspect, so we have to redo this. But while we thought it was working, the observed force was about 0.1 newtons per kilowatt, which was very exciting to us because ion drives, the kind of engines that satellites use, are only about 0.02 newtons per kilowatt. So this was about 10 times better than the industry standard engine.
But why do you say without the need for fuel? Because you have to have a laser.
Yes, but that's not fuel because you can power a laser from a solar panel.
Okay.
I guess I should really say without propellant. I mean, you could say maybe electric power is fuel, but what I mean is that, you could launch a satellite which doesn't need heavy fuel on board, just a solar panel, and it won't run out of fuel either. The solar panel will last for a long time.
And when you say it's a fiber optic loop, you mean it's like an electromagnet, like it's got 1,000 loops, or it's got 1 or 2 loops?
This particular one had 300 loops in a coil shape.
Because the laser is light, though, and it's obviously speed of light is always going to be constant. With Unruh radiation, you have to have acceleration, don't you? How does that work with light? Am I just overthinking this?
Well, no, it's a good question. So I'm assuming photons are particles and that they carry inertial mass, which they must because they carry energy, so they must have inertial mass. So I'm treating them like particles here.
Oh, okay. Oh, interesting.
Okay, so there's that Spanish experiment, and then there was a third way, which turned out to be, well, we think 1,000 times better. So at the same time these experiments were going on, I was negotiating with an electrical engineer. This electrical engineer called Frank Becker contacted me in 2017. He'd read my papers on quantized inertia, and he remembered an experiment he did many years earlier, trying to reproduce the Bielefeld-Brown effect, or Thomas Townsend-Brown effect, which was the capacitor experiment I mentioned earlier. The capacitors with sparks discharges move towards their anode. And he thought that could be evidence for quantized inertia. So I talked to him and liaised with him on an experiment, and then he received funding and experimental help from somebody who's actually an actor called Bhatt in Hollywood, who's an actor, but he also has an MSc in mechanical engineering, and he had some money too because he's an actor. So he funded it, and they did some experiments and they published their results on the archive here in 2018. So their experiment looked like this. They had a DC power supply about 5,000 volts. So you see, I can talk about this experiment far more because there aren't any lawyers involved. So 5,000 volts in, there's a circuit transformer, and then they put a capacitor in a vacuum sealed container and a Faraday cage to block the electromagnetic radiation, keep it in there. And they put it on a digital scale, and they charged up the capacitor and made it emit electrons in field emission. So there are electrons slowly drifting through, and the capacitor had a dielectric between the two plates as well. Okay, and the results are shown here. So the separation between the plates is shown on the x-axis, and the force is on the y-axis. So the data is the red dots. So you can see that for a separation of about 1 millimeter, I didn't actually have any data there, but for about 0.1 millimeter, the force is going to be about 100 micronewtons. And then going down to about 10 micron, here they got a force of about 10 to the minus 2 newtons, which doesn't sound like much, but given the power they were putting in, this amounted to 100 newtons per kilowatt. So given that the Spanish had produced 0.1 newtons per kilowatt, this is 1,000 times better. So this was obviously extremely interesting. So they published this on the archive, and their names are Becker and Bhatt. Okay, so the explanation as to what's going on using quantized inertia is like this. So normally, the upper plot here, the upper schematic shows an electron accelerated to the right. Now, normally in quantized inertia, as I said before, there's more Unruh radiation in front of the electron because there's no boundary except the Hubble boundary. So I've shown it as orange because the radiation field is warmer or more energetic. Behind the electron, there's less energy because some of it's been damped by this Rindler horizon, which is shown by the black line. Now, when an electron jumps out of the cathode of a capacitor towards the anode, it's different. Now it's got the same Unruh radiation behind it, but it's got virtually nothing between the plates because the plates have damped the radiation quite abruptly. So I've shown it as white here. So now the inertia of an electron has actually reversed, and the Unruh waves are pushing it forwards with the acceleration. So it's as if it's got a negative inertial mass. So the electron gets an extra boost, and it hits the anode and pushes the whole capacitor forward. So that's the theory. And so I derived the force from quantized inertia, and it looks like this. So the force is the number of electrons you've got times the Planck constant, reduced Planck's constant, times the speed of light, divided by the separation squared. And this shows the data. So this is the separation on the x-axis, and the y-axis shows the force. And the data is shown by the black diamonds with error bars, and the prediction is the red squares, and it agrees with the data, as you can see, quite well. So this looks slightly different to the other one, because the other graph had a log scale on the y-axis, whereas this one has just a normal scale, so you can see it's exponential. So this means we could get even more thrust if we use narrower plates, plates closer together. Okay, and it's exponential as well, so we can make a real big difference. Okay, so they did some other experiments as well. They tried thickening the cathode of the capacitor, which, according to the theory, should reduce the force because it starts to damp the Unruh radiation here now, and it did actually reduce the force. And then they did something very interesting. They tried a metal plate in all sorts of positions in front of and behind the Rindler horizon, and they found that when they put it behind where they thought the Rindler horizon should be, which is about 2 centimeters from the capacitor, the effect of it disappeared, as if it wasn't visible to the electrons anymore. So the force, which is shown here by this bar, first reduced with these bars, and then it came back to the original size here. So this is a very nice, crucial experiment for quantized inertia, and it may be the first direct observation of a horizon, a Rindler horizon, that's been made. Okay. So just to give you an idea about what this means for the satellite industry, if we can confirm it, it would revolutionize it. So imagine you have a satellite here with a horizon drive on it, and a solar panel. The mass of the panel is 20 kilograms. The mass of the drive is 10. So it's got 300 newtons pushing down. The output of the solar panel would be something like 0.25 kilowatts. The horizon drive gives you 100 newtons per kilowatt, so we're going to get 25 newtons, which is about 8% of its weight. So present satellite ion drives give only 0.02 newtons per kilowatt, so this is much bigger than that. It's about 10,000 times bigger. And then we can also, if this is confirmed, we can launch things with it. We can make them levitate and launch. So here's a horizon drive of mass 10 kilograms, and let's say we use one of the new lithium air batteries with a mass of 1 kilogram, producing 1.8 kilowatts. Total weight down is 110 newtons, and the total force up is 180 newtons. So that's more than its weight. So this enables launch and levitation, so we can have electric rockets. Okay. So I'll just conclude now and say that quantized inertia explains inertia for the first time. You can derive it from the Heisenberg uncertainty principle or from information as well. The theory can be derived that way. It unifies relativity and quantum mechanics. It gets rid of dark matter and dark energy as well. There's extremely good astronomical evidence for it, really good evidence. It predicts what you might call a horizon drive or an electric rocket, and experiments are continuing where we're going to set up an experiment similar to the Becker and Bhatt one at Plymouth and try and enhance the effect, and DARPA have agreed to fund this new experiment. And if verified, this means we can have fuelless satellites, electric rockets, and also it enables interstellar travel in a human lifetime for the first time, because normally, say if you want to get to Alpha Centauri in a human lifetime, you would need to get close to the speed of light. And to do that with rocket technology, you would need a mass of a minor planet of fuel. But this form of propulsion doesn't need any heavy fuel. So you could actually go to Alpha Centauri within a human lifetime. Okay, so the basic takeaway is that quantized inertia says that all movement is caused by horizons in a quantum vacuum, making gradients in it. So let's design technology that taps into this. Okay, so thank you for listening. I've published a book about this, but I admit it's quite expensive, so you may prefer to read my blog, which is also called Physics from the Edge. You can email me with questions here. I'm on Twitter as Emmy McCulloch, and if you want to see another talk of mine, you can look at this TEDx one here. Thanks for your attention.